Hello, everybody.
It's MoNaCo.
And
And we're talking about physical behavior matter. This is our 8th video in the unit.
yeah, 8 of 9. We almost done.
So this is a background information video. There's no calculations in it, but there are facts that you should learn in relationships that are important related to the behavior of gases.
Right, and what those gas laws are.
I'm not talking about gas that you put in your car.
No. The phase gas.
Phase of matter, the gases.
Right.
So,
That's gas in your car. That's just short slang for gasoline.
Right.
All right, cool. First, kinetic molecular theory. Got some postulates.
Mm-hmm.
Right?
We call it KMT sometimes.
Yeah, I would call it KMT.
And there's rules.
Sure, and we're going to use this a lot. This
The
KMT
points.
stuff. Yes. Gas consists of a collection of small molecules, specifically going in a straight line.
We also assume that those molecules have no volume. That is, they're behaving like points in space, which isn't really true, but it's part of KMT.
True. I mean, in reality is, right, the amount of volume they have is so negligible.
Compared to.
Right.
It's like me standing on a scale losing one hair off the top of my head going, well, I know I am lighter now, but it can't be measured.
Right. Collision between these molecules are perfectly elastic, which means the energy is neither gained nor lost during the collision. Again, not 100% accurate, but this is the idea.
Right. But those collisions create pressure, and that's why we were talking about that before. And also, we assume that the atoms or the molecules of gas are not sticky. They have no attractive or repulsive forces between other molecules of themselves or the walls of the container that they're contained in. They are magically frictionless kind of things. So
right. I like to say they can't feel their neighbors.
Yeah.
They can't feel each other. And so this is what kinetic molecular theory was started as.
Yeah, basically it's like, there's some laws of physics that we're going to kind of choose to ignore when we describe the behavior of a gas.
Sure. Well, these ideal gas theory applies to gases. Basically, the more they act like the conditions of KMT, the more ideal
it will be.
And predictable.
Right. And ideal is that most predictable, most desirable gas that you can base math on, that you can use math with.
Right, and we want to do some more math.
And that's what our last video will be.
Cool. So conditions that make it behave like an ideal gas.
So if you got to get close to kinetic molecular theory, you got to have small molecules. So like hydrogen is the best, most ideal
hydrogen,
gas.
Helium,
H2,
much
then He,
smaller in diameter than say chlorine gas,
or some larger covalent molecule that's gas, SO2 or something like that. CO2.
Right.
Bigger molecules, less ideal.
Correct.
Next, you got to have a high temperature because that causes them to move in straight lines more.
Right. Well, and think about it too. If I'm moving fast,
you're not going to get stuck to anybody or any walls of containers.
Right. And I'm not next to my neighbor long enough to even feel them.
Right.
If I could feel them. Right.
And low pressure, which helps these molecules of gas spread out more.
Right. The farther I am apart,
less likely you are to, 1, bump into a neighbor. 2, if you do, they're not going to stick because you're moving very high, fast, speedily. And 3, you're really small. So, that is how, these are the conditions of a gas behaving most like an ideal gas.
Right. And you're going to hear a question like that, I'm sure.
Guaranteed.
Under
which set of conditions would H2 behave most like an ideal gas?
Very, very well said.
And you would say high temperature and low pressure.
That's it. That's it right there. High temperature and low pressure.
Facts.
Perfect. All right, so let's get into the actual laws.
Which we will then combine and use in our last video. So these each are hidden and folded into the law that we end up using. But we got to tell you about the truth.
Yeah, and we're going to
skip them.
Yeah, we're going to do them one at a time. I didn't put these out in algebraic form, though.
No, we didn't put the equation out because we used all those in the final equation. We're not going to
derive it all together. Yeah.
So these are just logic and graph relationships.
Right, and some of these are actually going to have logical.
You already know.
Yeah. So first part is, of course, constant volume. So the volume doesn't change. That's key here.
So the relationship between pressure and temperature. So if you change pressure or temperature, what happens to the other one?
Sure.
So as a temperature increases in a confined space, like inside of a soda can or something, the pressure will also increase.
Right, and it makes sense because temperature is kinetic energy.
And pressure is a measurement of how frequently and how energetically atoms hit the walls of the container.
Right, so the faster we get them going, the more collisions with more force.
So, it makes sense. And so I bet you the opposite's true as well.
That is true. So as I decrease the temperature in a confined space,
pressure is going to drop.
pressure is going to drop. Now, we call this kind of a relationship mathematically
Direct.
a direct relationship,
One goes up, the other goes up.
and you're going to need to know the graph.
And
the graph is going to look something like
temperature versus pressure.
Right.
And it's going to be a straight line.
straight up like that. As one goes up, the other goes up. Direct relationship.
All right, let's check out Charles' law, which is at constant pressure. So no longer constant volume, but at constant pressure, which is harder to control, by the way. The relationship between temperature and volume.
As temperature goes up at a constant pressure, the volume will also go up.
So if I heat up a balloon that has air in it, it's probably going to expand.
Correct.
It would be odd if there was some kind of thing you could ride around in that would help that on it. Oh, wait, a hot air balloon.
Yeah,
You
right.
heat up the air, the balloon inflates, and it carries you up in the basket into the sky.
You see?
So as temperature decreases, the volume will decrease.
Okay, so again, very direct relationship.
So temperature versus volume, another straight up line.
Another straight up line.
Higher, higher, lower, lower.
So these two are pretty good. Pretty
Very
as far
good.
as logic goes,
Simple.
I think we can get our heads around
The
those.
next one is going to be Boyles Law. So this is constant temperature, volume, pressure relationship.
I'm not going to change the temperature now at all.
No, which is again hard to do in reality, but as pressure increases at constant temperature, the volume will decrease. How can we think about that? So as pressure increases,
So I'm going to
volume goes
squeeze
down.
it.
So okay, so this is kind of like a car cylinder or a piston in an engine. If you push it down, all the air that was in there gets squeezed, the volume decreases, the pressure inside that part of the piston that's still in there
It's got to increase.
has got to go up.
Because the number of collisions is going to go
Up.
up.
And it's like a syringe where you're holding the end and squeezing,
Sure.
you know. So as pressure decreases, the volume will increase.
Good. Now
Or
this
vice versa.
particular thing now is called an inverse relationship.
So they're opposite. As one goes up, the other one goes down.
Right. So
One
you
goes
got
down,
to
the
know
other goes up.
you got to know that this curve goes down.
Down. High pressure means low volume. Low pressure means high volume.
There you go.
Cool fact about that one, those weather balloons they put up there to see what it's going to be like and stuff, they start out on ground at very small. As they go higher in the atmosphere, the pressure gets lower and they get really, really huge.
Big, yeah. They got to know that's coming or it's going to burst.
Yeah, and that's how they get their instruments back. It literally bursts and it falls back down. But
Nice.
I digress. This other law called Avogadro's law. Recognize his name, don't you?
Yeah. Yeah. He had a number, didn't he?
Amadeo Avogadro and his moles.
Yes.
Right? Well, this is the nature of where that number came from, because if you take different types of gas that have the same volume,
Same
at
pressure.
the same pressure, and the same temperature,
Then they will have the same number of moles or
molecules of gas.
There you go.
It's got to only be a gas. It doesn't work for solids or liquids.
Nope.
Only works for a gas. That was Avogadro's original law. And then some 100 years later, when the calculus was worked out, they figured out, okay, that relates to 6.02 times 10 to
Sure.
the 24th.
And a lot of trial and error with that one too.
Avogadro's first mole was much more usable, 22.4 liters of gas.
Sure. And I want to make sure we remember that because we didn't do that a lot when we were talking
No.
about the mole.
No.
But it's going to come into play a little bit more here.
Okay.
Okay.
So equal volumes, equal temperatures, equal pressures must have the same number of molecules, regardless of their size.
Right. Easy enough.
So this
Oh,
equation
my
here, we
favorite.
love it so much. I remember doing this in high school so much back in the 90s.
I used to call this Pivnert
Pivnert.
because
This-
now that N is number of moles.
Let's have a moment of silence for Pivnert.
All right.
Thank you for mourning the loss of the ideal gas equation.
And unfortunately, New York State says we don't have to do it anymore. So there's all that
Right.
algebra.
Algebra, brah.
We don't get to do.
Algebra, bro.
But
Yeah.
let's look at the Big Mac Daddy, the combined gas law that I'm not going to derive for you
No.
from Pivnert, which
But
I could.
He could.
Oh, I could.
I believe
This
it.
is it, and this is in Table T.
He did it earlier.
P1 V1 equals T1. Yeah, he said, Milks, you're doing too much. Equals P2 V2 over T2.
So
Now, what you need to know here is that
this is trying to relate the states of two conditions on the same sample of gas.
correct.
Basically what it's saying is that the initial pressure, volume, and temperature relationship and ratio is got to be equal to the final pressure, volume, and temperature
Right.
relationship and
And
ratio.
all of those laws that we just did at the beginning with the little graphs are hidden in here.
Right.
So if I were to increase pressure, the volume would have to go down.
And the temperature would do also some changes,
Possibly.
possibly.
And the nice thing about this is if we hold something constant, we can cross that piece out if you want.
Or I'll be teaching you just write it over as the same number.
You can do that too, which adds just a little extra math. But
Nah, not
you know.
gonna hurt you.
right.
And so what we'll be doing in the next video is we'll be using this ideal gas, or the combined gas law. See, I'm stuck on ideal gas. And we're going to use the combined gas law to find one of the missing variables.
Right.
So let's just do a little more logic and reason to wrap it all up.
Okay.
Okay. So pressure-temperature relationships.
Okay, so this is, I don't see volume, so volume's got to be held constant.
Right.
So the relationship, let's think of something with the constant volume. An aerosol can.
That's why you don't throw it in the fire.
Right, because if I heat it up, what's going to happen to the pressure
temperature is going to
inside?
go crazy.
And the pressure eventually is going to
Pop!
pop. Right, so temperature, volume's got to have pressure.
It's like you're taking a balloon
Constant.
and you toss it in the freezer. It's going to get smaller.
Right, because the particles inside are going to move slower,
and not create as much.
collisions and pressure.
Right.
Right.
And the volume as a result is going to
There you go.
volume pressure. So this is like that engine cylinder I was telling you about, or a syringe. Like you seal off one end of it, and you push the syringe in. If you're changing the volume, you're trying to squeeze it down,
The
you're going to build
pressures.
pressure up inside.
It's got to change.
Or like the engine cylinder is the same idea.
Yes.
Okay.
Okay.
And the last little one, number of moles of gas particles relationship. Basically, like when you're blowing up a balloon, you're putting more moles of gas into the balloon,
Sure. Same with the tires.
and it expands. So the volume would increase for one.
Yep.
And two, the pressure would also increase. So you get a flat, it's because you've lost some gas out of your tire. You fill it up, creates more pressure, increases the volume. It's got a few relationships built in there. That's why we didn't just say if then.
Well, you would think that the volume of a tire, if you think about it, if it's not like flat against the ground, it's got a
Constant volume.
yeah. And so if you
But
just
they
keep
do
adding more stuff, that
expand the-
pressure goes up.
Yeah, and they
At
will
some point,
expand as a result.
Yeah.
I mean,
there's some resistance to that.
So logic and reason is going to get you through most of these general kind of relationship statements.
yes.
The maths is what we're going to hit up in the next and last video of the
That's it.
unit.
So there you go. Some of these relationships are very instinctually logical. Some of them you might have to think about if they don't make sense to you. But at the end of the day, we need to know them all. Drawing those little graphs is key. Hey, see you guys.
Peace.